Hello, this is the video demonstration for my final year project. My final year project is lupus nephritis class classification using vision transformer. Class classification means in the glomeruli level. So lupus is an autoimmune disease which attacks your own healthy organs by your own immune system. It mistakenly attacks it. And lupus nephritis is when it attacks your kidneys, and these kidneys have filters called glomeruli. These filters gets damaged because of immune deposits, and the and these these damages can be seen on those glomeruli, and each damage has a specific pattern to identify. So there are 6 classes in lupus nephritis. From that, I use only 4 classes. The first class, the minimal class, which the glomerulus looks almost normal. Then the mesangial hypercellularity, the second class, which shows increased cellularity. And the third and the fourth class are combined because it both shows proliferative changes. And the fifth class is the membranous pattern that shows the membranous thickening. And the problem in diagnosing these classes in lupus nephritis, for pathologists it's time consuming. It takes a lot of time for them to identify these changes, these patterns in one glomerulus. And it all depends on the pathologist expertise and experience. And it takes so much time and expertise to find where the changes happen, in which region the changes happen. So in my project, if we take a look at the research gap, before I found a research paper that aligns with my project really close, but it uses a CNN model, and it uses mouse kidneys and categorized into 3 classes: control, class 1 and 2 combined, and class 3 and 4 combined. And they used 26 mouse kidney images and got 94.5 accuracy. And most of these renal pathology research, AI model researchers use CNN based models, and most studies use only one stain, a single stain, and no human kidney image. There are some, but most of the research I've seen, they've used mouse kidney datasets. And in my project, I'm using a vision transformer to categorize these, and I'm using human lupus glomerular images, and these are categorized into before mentioned 4 classes. And I'm using multi-stain images like HNE, PAS, and silver staining. And I'm using a web UI to make it simple to just to upload and click a button. You can categorize these images. So if we look at the solution I've created, this is the design architecture and the algorithm, the order I'm using. So in the first layer is the data tier, and in there I'm using 382 glomerular images, human glomerular images. I've categorized these into those 4 classes using the help of a pathologist from Colombo pathology department, and it that pathologist gave me some images from the department too, but it was really limited, and the pathologist helped me to identify the images from online sources too, but it was really hard to find exactly lupus nephritis glomerular images. And in those images I'm using HNE, PAS and silver stains. There are 1 or 2 trichome stain images, but it was not practical for this type of training, because VIT might sometimes get confused with all the colors. So HNEPAS and silver all go near pink to purple color. So I'm using 17-15-15 ratio to split the data set. So I'm using a dataset split script for that. After I upload images to those the folders that contain all the images, it split to this ratio into train, validation and test folders. And then I'm using augmentations such as random cropping, flipping, color jitter, Gaussian blur and random erasing. And I'm using class weighted loss for class imbalance, because membranous class only have 71 images. That's the lowest categorized images. And if we go to the model tier, I'm using a vision transformer based 16 pre-trained model from ImageNet on ImageNet, and I'm freezing the backbone to fine tune because of the less number of images that I have, and has a custom head of dropout 3.0.3 plus linear 768 to 4 batches, and I'm using Adam optimizer and cosine aligning LR plus the gradient accumulation, and 4 lupus nephritis classes in the model tier. So if we go to the application tier, those after all the training happens in the model tier, the application tier is a UI and the backend, and I'm using Flask to make a Python backend and use the model to run on the backend and show the data on the UI using HTML, CSS and JavaScript. I made a single web page for that, and I use drag and drop multi-image upload, and I'm showing some cards as the results with confidence bars and all the probability breakdown, because there might be some classes that have other features too. It overlaps sometimes, and in these classes the confidence is color coded. If more than 80% is green, it's between 50 and 80 is orange, and less than 50 is red. So these are the performance metrics before I go to the live demonstration of the code. So average of 70% accuracy has seen on the unseen images, and with a macro average of 0.917, and the membranous class got 100% accuracy, because because of the less number of images, I've blocked some of the images in the mesangial pattern. So sometimes the mesangial pattern gets confused with the proliferative and other classes because it has the same pattern can be seen in the other classes too. So overall test accuracy is 67.2. So let's go to the code. So this is the transform.py. In here all the augmentations happen, the resizing, the color jitter and those things. And in the train, this is the train loop happens in here. Before I use 20 epochs, now I'm using 30. I used 30 epochs for the last training because it actually improved the accuracy. And for the class counts, I'm actually reduce the mesangial class to 60 to boost the its penalty weight because of the confusing mesangial and proliferative class clash. And the unfreezing the last 6 blocks in the transform model, that's for fine tuning and a lower learning rate for fine tuning too. So in here happens all the training loop, and it gets saved to this pth file over here. And if we look at the model, I'm using the Vision Transformer patch 16 224 model, and it's a pre-trained model, and I'm starting with a frozen backbone. And if we check the other files, this is to show the confusion matrix and all the other testing, all the accuracy numbers and testing things, ROC curve, like that. And this is the predict class for the predict file for the before I created this app.py and the web UI, and this uses a Kinter UI, and it was not user friendly, so I moved it to a web app. So in split dataset, I'm splitting the classes to the before mentioned ratio, the 70-15-15 ratio. And in app.py, this is all the inference happens, and the model runs on the back end, and it shows the results on the sends the results to the UI, where the UI I created just single HTML file to show the class classification. So let's run and see. And this is running only on a personal computer which uses an consumer graphics card. So let's run this. This is how the this is the UI. You can see, you can just drag and drop some models. These are some untrained, these are some images that the model has never seen. So you can upload multiple images like that and just press this button and you can get the results here. As you can see, the membranous pattern, these patterns get, this pattern got 81.3% accuracy, and he is showing a little bit of hypercellularity here. And in this is also a membranous pattern. As you can see, these walls are thicker than in this one, and it is showing a little hypercellularity, and yeah, it's showing some proliferatives too. This is the almost looking normal class. As you can see, all the walls are thinner than these classes, and it got a 77.6 accuracy. And this is a mesangial hypercellularity, which means the second class. As you can see, a number of there are more number of cells than in here, and or even here, and there are some proliferative changes here. And this is, and it got a 54.4 accuracy because there are some other features can be seen too, and it's overlapping with the even in this there are some overlapping features, but it's mostly look like a normal one. And this has got a 90% accuracy because you can see this everything looks proliferative, and it's shown even proliferative classes. You can actually see a little bit of hypercellularity too. So this is a positive test case, and I had to show that this model didn't don't have a validation to identify what is a glomerular or not. Even if I add this, it will identify, but it will show a low accuracy rate. And if we use a lot of images like this, set this, some might show, some classes are correct. Yeah, these are proliferative, these are minimal. These look a little normal to me, but it shows membrane, maybe because of the membrane. It can be seen because of the stain, and this shows a lower, it shows a lot of combined, and yes, there are some overlapping features, and there are some images that gets wrong because of the limited number of data sets, and the main reason is the overlapping features. So that is my demonstration of the project. Thank you.